Hi, my name's Dan, and this video is one in a short series of videos which are charting the creation of a 4-bit CPU in a digital simulator called DigitalWorks. When I say a short series, actually there's quite a long series going on, but it's been split into shorter playlists. This is the final playlist in this larger scheme of things, in which we're putting things together, creating a 4-bit CPU in DigitalWorks, which is a simulation software for digital electronics. And we're going all the way through from the basic gates to creating a working programmable 4-bit CPU. So in the wider scheme of things, there's a roadmap of where we're going in the description down below. We're getting quite close to the end now. And also down below, there is a link to where you can get the DigitalWorks software for free. It is free to use. If you're just dipping in at this point, quite a lot of things in this last series won't necessarily make a great deal of sense to you because this is a pyramid of understanding. Towards the beginning, we were doing quite generic stuff with multiplexers and decoders and things like that. Now towards the end, we're very tied into a specific CPU design. However, this particular video, we're going to create the last component that we need before we can put everything together, which is a ring sequencer. While there would be other ways of doing this, ring sequencers are quite a generic thing. So this particular one is quite generically usable, as it happens. So just a quick reminder of what we want from a ring sequencer. We've actually got our CPU architecture is going to expect to have 6 control lines, each of which will get a signal, as in a high pulse in a row, and they are to control the fetch, execute, and increment cycle of the CPU. And we need 2 for the fetch, so we call those fetch 1 and fetch 2. We need 2 for the execution, which we're calling x1 and x2, and we need 2 for the increment, which we're calling inc1 and inc2. And what we want is a system which will create these pulses into the 6 lines that we've got one at a time in sequence, and then go back to the beginning. It's easier to create an 8-bit one than a 6-bit one, as in a set of 8 lines, for fairly obvious reasons when we get into it. We're going to use existing components. This is quite wasteful in terms of gates. So A, I don't care, because keeping things simple is good, and B, because this is a simulator, there are some particular issues with timing. It would be possible to do this using the timing of gates, using basic flip-flops, but that's harder to do in the simulator. So actually, what we're going to do is we're basically going to use a counter and then plug that into a decoder. So somewhere we've got a control 3-bit counter, and way back in time when we made a 3-bit counter, you might have been wondering why a 3-bit counter, not a 4-bit counter. And the reason is because this is what we actually created it for. And the 3-bit counter is the only piece that we've got that actually doesn't just use basic gates, it uses some of the built-in flip-flops that DigitalWorks have got. And it uses these JK flip-flops, which have been dragged in from here. And the reason is, again, down to this issue with the disparity between timings in a simulator and timings in actual electronics. So we've got a count in 3 bits, and then we've also got a 3-bit decoder. And you might have wondered why we went through the process of doing all these different decoders: 1-bit, 2-bit, 3-bit, 4-bit. And the kind of hidden agenda there was that the 3-bit decoder is what we're going to need for this ring sequencer. We have some controls here, which are clock. We're going to actually build the clock into the sequencer. There's no reason why not. And link that up. And while we're here, we do want these controls. We want to be able to say go and reset on our counter. It's going to be really useful in terms of controlling the CPU in an overall way. And then now we need to check that we've got these going right. We want two to go to, so the top to go to the right hand end. Once you've done one, it tends to become easier to do the others once you've thought about it. So it kind of does this kind of crossover pattern there. And then we've got the output. So we've got 0 to 7. And that's basically all that we need to do to create a ring sequencer. We're going to put 8 outputs on there. Okay. And then when we test it, I'll show you how we can actually adapt this to make it a 6-phase sequencer rather than an 8-phase sequencer, which is pretty straightforward. We won't actually do that for our CPU. We will just use it as an 8-phase. But let's templates. I keep forgetting that, and for some reason I am not in a place where I can use the templates editor. That's because I've been looking at some other circuits and I'm kind of inside a macro here. So just to deal with this, I'm going to copy that, close the macro. Let's see what we had. Yes, we have the output from previously and my old ring sequencer that I was looking at. So just delete all that stuff. Sorry about that. Pretend you didn't see that. Okay. Or as Hagrid says in Harry Potter, I shouldn't have told you that. Right, we should now be able to do the template editor. And this looks very different from what we want. Let's change that. Annotation. So we're going to call this ring sequence 8. 8-phase. Okay. That's a longer name, so we're going to need a longer box. We're going to need a bigger boat. And we're going to have 3 controls. I'll put the controls in on the right-hand side. And we're going to want 8 outputs, which I'm going to put at the top. Which is unusual for outputs, but there is a logistical reasoning going on here, which is that when we plug this in to the other components in the CPU, actually, if you remember the diagram that I had, I actually showed the ring sequencer being below everything else, and then sending the signals upwards. And so there's no reason why we can't actually, when we actually put it together, have a very similar layout to that diagram. And so I'm going to make that more possible by setting this up in that sort of way. Right. Could make it a little bit shorter. Do I want to? I don't really care. In fact, if anything, to make that centered, I'm going to make it longer. And I'm just now being a little bit picky, but I'm going to separate these a bit more to give them a bit more room. And let's do a bit more labeling. So this value is wrong. We need to change that. But this is... I put in 3 because we've got the clock, and I didn't think about the fact that actually our clock's internal. So I'm just going to get rid of that one. We actually only need 2 commands here, which are go and reset. So they're commands that we built into the 3-bit counter, and go needs to have a constant high signal to actually be running, and reset will set it back to zeros, which is going to be very useful. Reset. And finally, change this to edit annotation. We're going to call it phase 0 to 7. And what we're going to do is we're going to count along from 0 to 7. So this is kind of the opposite way around. If you've been with me all the way along, you'll hopefully be used to this by now. When you're doing a binary number and you're doing it in pins and it's horizontal, then you tend to have that in the order in which you would go. You would write it as a number, which is with the most significant bit at the left-hand end and the least significant bit at the right-hand end. But when you've got discrete lines, you tend to do what conceptually is sort of the opposite, which is you have the first one, you have 0 at the left-hand end and count up to 7 or however many you're going to at the right-hand end, it's just conventions that work with the way we read English from left to right. So let's do the pin connecting up thing. And I'm asking myself at this point whether you're going to get the privilege of having the fast forward and the music. And I've talked through some of this, so the answer is no. Sorry or congratulations. It depends on whether you like that music or not. And you may have liked it at the start, but we've had it quite a lot in this series of videos. Nearly there. I feel the need to keep talking whilst I'm doing this wiring up, and I'm not sure what I'm going to talk about. It's a nice sunny day here where I'm creating this in Northumberland in England, where still somewhat under some COVID restrictions. It's 2021 and we're in the middle of June, actually near the end of June, and I'm creating these videos with a view to using them in teaching in the autumn. Just, if you wanted to know that. These videos are actually being created for university course teaching, but I'm making them publicly available. So if you're not a Northumbria University student, welcome. I hope you're enjoying these things. And I've surpassed my wiring up there. So save, and we need to test it. So save as. We're in my macros, and this is the ring sequence 8 phase. So let's do a new circuit and pull that in. Where did it go to? Ring sequencer 8 phase, near the bottom. And so obviously a couple of controls here. Go and reset and chuck in the LEDs to show this. So what should happen is that these should light up as the clock goes. These should light up in turn from left to right. When we say go, I'm going to be intrigued to see what happens when we actually start, to see what number we start with. Start with 0, 1. Okay, so I hit reset. Yeah, so we're always going to have one high. I'm thinking about binary numbers where it's all going to be low, and I expected them all to be blank, but actually, because it's a ring and it's a sequence, there should always be one, and it's the 0th one that will happen by default. So let's click go, and hopefully, Bob's your auntie, off we're off. And, so the clock is going fairly slowly. Let's just up the clock speed to see that going faster. Let's go 50 Hertz. There we go. Oh, how pretty. It's like a disco strobe light or something. Let's set that back. phase. Right, now at this point, I can see that that's working. And I did just make a little promise, which is that I'm going to show you how this could be done as fewer than 8 phase, which is actually pretty straightforward, which is we're going to take off that control there, and let's turn it into a 6 phase. I'm going to take those off there. And all we do is we take the 7th phase and link it back to reset. And so we've lost our reset. We could also add a control on there to do the reset, but it would need an OR gate to be able to work properly. But let's see this working. 4, 5, 6, 1, 2. Because what happens is when it hits that 7th one, it immediately resets and so sets it back to the first one. So that's how you can make a 6 phase sequencer, or in fact you can make a 2 phase, 3 phase, 7 phase, anything up to your 8 phase using the 8 phase sequencer. However, when we actually put this in for no huge reason, we're just going to use it as an 8 phase rather than as a 6 phase. I think I might change my mind later on. So that's the last of the components that we needed to make in order to make our CPU. So for the next few videos, we're actually just going to be bringing the components in and wiring them up and getting them in. We're getting really close to the end now. So I'll see you in the next video. That's it from me for now.